10 Things Einstein Got Right. 100 years ago, on May 29, 1919, astronomers observed a total solar eclipse, in an ambitious effort to test Albert Einstein's general theory of relativity by seeing it in action. Essentially, Einstein thought space and time were intertwined in an infinite fabric, like an outstretched blanket. A massive object such as the Sun bends the spacetime blanket with its gravity, such that light no longer travels in a straight line as it passes by the Sun. This means the apparent positions of background stars, seen close to the Sun in the sky, including during a solar eclipse, should seem slightly shifted in the absence of the Sun, because the Sun's gravity bends light. But until the eclipse experiment, no one was able to test Einstein's theory of general relativity, as no one could see stars near the Sun in the daytime otherwise. The world celebrated the results of this eclipse experiment, a victory for Einstein, and the dawning of a new era of our understanding of the universe. General relativity has many important consequences for what we see in the cosmos and how we make discoveries in deep space today. The same is true for Einstein's slightly older theory, special relativity, with its widely celebrated equation E=mc². Here are 10 things that result from Einstein's theories of relativity. 1. Universal speed limit. Einstein's famous equation E=mc² contains c, the speed of light in a vacuum. Although light comes in many flavors, from the rainbow of colors humans can see to the radio waves that transmit spacecraft data, Einstein said all light must obey the speed limit of 186,000 miles, 300,000 kilometers per second. So, even if two particles of light carry very different amounts of energy, they will travel at the same speed. This has been shown experimentally in space. In 2009, NASA's Fermi Gamma Ray Space Telescope detected two photons at virtually the same moment, with one carrying 1,000,000 times more energy than the other. They both came from a high-energy region near the collision of two neutron stars about 7 billion years ago. A neutron star is the highly dense remnant of a star that has exploded. While other theories posited that space-time itself has a foamy texture that might slow down more energetic particles, Fermi's observations found in favor of Einstein. 2. Strong lensing. Just like the Sun bends the light from distant stars that pass close to it, a massive object like a galaxy distorts the light from another object that is much farther away. In some cases, this phenomenon can actually help us unveil new galaxies. We say that the closer object acts like a lens, acting like a telescope that reveals the more distant object. Entire clusters of galaxies can be lensed and act as lenses too. Sometimes, when a distant celestial object is precisely aligned with another object, we see light bent into an Einstein ring or arc. In this image from NASA's Hubble Space Telescope, the sweeping arc of light represents a distant galaxy that has been lensed, forming a smiley face with other galaxies. 3. Weak lensing. When a massive object acts as a lens for a farther object, but the objects are not specially aligned with respect to our view, only one image of the distant object is projected. This happens much more often. The closer object's gravity makes the background object look larger and more stretched than it really is. This is called weak lensing. Weak lensing is very important for studying some of the biggest mysteries of the universe, dark matter and dark energy. Dark matter is an invisible material that only interacts with regular matter through gravity, and holds together entire galaxies and groups of galaxies like a cosmic glue. Dark energy behaves like the opposite of gravity, making objects recede from each other. Gravitational lensing in general will also enable NASA's James Webb Space Telescope to look for some of the very first stars and galaxies of the universe. 4. Microlensing. So far, we've been talking about giant objects acting like magnifying lenses for other giant objects. But stars can also lens other stars, including stars that have planets around them. When light from a background star gets lensed by a closer star in the foreground, there is an increase in the background star's brightness. If that foreground star also has a planet orbiting it, then telescopes can detect an extra bump in the background star's light, caused by the orbiting planet. This technique for finding exoplanets, which are planets around stars other than our own, is called microlensing. NASA's Spitzer Space Telescope, in collaboration with ground-based observatories, found an ice ball planet through microlensing. While microlensing has so far found less than 100 confirmed planets, WORST could find more than 1,000 new exoplanets using this technique. 5. Black holes. The very existence of black holes, extremely dense objects from which no light can escape, is a prediction of general relativity. They represent the most extreme distortions of the fabric of space-time, and are especially famous for how their immense gravity affects light in weird ways that only Einstein's theory could explain. In 2019, the Event Horizon Telescope international collaboration, supported by the National Science Foundation and other partners, unveiled the first image of a black hole's event horizon, the border that defines a black hole's point of no return for nearby material. 6. Relativistic jets. This Spitzer image shows the galaxy Messier 87, M87 in infrared light, which has a supermassive black hole at its center. Around the black hole is a disk of extremely hot gas, as well as two jets of material shooting out in opposite directions. One of the jets, visible on the right of the image, is pointing almost exactly toward Earth. Its enhanced brightness is due to the emission of light from particles traveling toward the observer at near the speed of light, an effect called relativistic beaming. By contrast, the other jet is invisible at all wavelengths because it is traveling away from the observer near the speed of light. The details of how such jets work are still mysterious, and scientists will continue studying black holes for more clues. 7. A gravitational vortex. Speaking of black holes, their gravity is so intense that they make infalling material wobble around them. Like a spoon stirring honey, where honey is the space around a black hole, the black hole's distortion of space has a wobbling effect on material orbiting the black hole. Until recently, this was only theoretical. But in 2016, an international team of scientists using European Space Agency's XMM Newton and NASA's Nuclear Spectroscopic Telescope Array, NUSTAR, announced they had observed the signature of wobbling matter for the first time. Scientists will continue studying these odd effects of black holes to further probe Einstein's ideas firsthand. Incidentally, this wobbling of material around a black hole is similar to how Einstein explained Mercury's odd orbit. As the closest planet to the Sun, Mercury feels the most gravitational tug from the Sun, and so its orbit's orientation is slowly rotating around the Sun, creating a wobble. 8. Gravitational waves. Ripples through space-time called gravitational waves were hypothesized by Einstein about 100 years ago, but not actually observed until recently. In 2016, an international collaboration of astronomers working with the Laser Interferometer Gravitational Wave Observatory, LIGO detectors announced a landmark discovery. This enormous experiment detected the subtle signal of gravitational waves that had been traveling for 1.3 billion years after two black holes merged in a cataclysmic event. This opened a brand new door in an area of science called multi-messenger astronomy, in which both gravitational waves and light can be studied. For example, NASA telescopes collaborated to measure light from two neutron stars merging after LIGO detected gravitational wave signals from the event, as announced in 2017. Given that gravitational waves from this event were detected mere 1.7 seconds before gamma rays from the merger, after both traveled 140 million light-years, scientists concluded Einstein was right about something else: gravitational waves and light waves travel at the same speed. 9. The Sun delaying radio signals. Planetary exploration spacecraft have also shown Einstein to be right about general relativity. Because spacecraft communicate with Earth using light, in the form of radio waves, they present great opportunities to see whether the gravity of a massive object like the Sun changes light's path. In 1970, NASA's Jet Propulsion Laboratory announced that Mariner 6 and 7, which completed flybys of Mars in 1969, had conducted experiments using radio signals, and also agreed with Einstein. Using NASA's Deep Space Network, or DSN, the two mariners took several hundred radio measurements for this purpose. Researchers measured the time it took for radio signals to travel from the DSN dish in Goldstone, California, to the spacecraft and back. As Einstein would have predicted, there was a delay in the total round-trip time because of the Sun's gravity. Then, in 2003, a group of scientists used NASA's Cassini spacecraft to repeat these kinds of radio science experiments with 50 times greater precision than Viking. It's clear that Einstein's theory has held up. 10. Proof from orbiting Earth. In 2004, NASA launched a spacecraft called Gravity Probe B, specifically designed to watch Einstein's theory play out in the orbit of Earth. The theory goes that Earth, a rotating body, should be pulling the fabric of space-time around it as it spins, in addition to distorting light with its gravity. The spacecraft had 4 gyroscopes and pointed at the star Im Pegasi while orbiting Earth over the poles. In this experiment, if Einstein had been wrong, these gyroscopes would have always pointed in the same direction. But in 2011, scientists announced they had observed tiny changes in the gyroscope's directions as a consequence of Earth, because of its gravity, dragging space-time around it. Bonus: your GPS. Speaking of time delays, the GPS, or Global Positioning System on your phone or in your car, relies on Einstein's theories for accuracy. In order to know where you are, you need a receiver, like your phone, a ground station, and a network of satellites orbiting Earth to send and receive signals. But according to general relativity, because of Earth's gravity curving space-time, satellites experience time moving slightly faster than on Earth. At the same time, special relativity would say time moves slower for objects that move much faster than others. When scientists worked out the net effect of these forces, they found that the satellites' clocks would always be a tiny bit ahead of clocks on Earth. While the difference per day is a matter of millionths of a second, that change really adds up. If GPS didn't have relativity built into its technology, your phone would guide you miles out of your way. 10 things Einstein got right.